Record. Okay, I'm recording now. I can stop talking about management. It's a joke. Okay. So now with this simple circuit, I've got the voltage across the DC supply. I have the voltage across the resistor. The only unknown voltage in that loop is the voltage across capacitor. So I can apply KCL, 240 minus 0 minus VC equals 0. The sum of the voltages around the loop equals 0. It's just KCL. 240 minus 0 minus VC equals 0, which means the voltage across the capacitor is also 240 volts. So we've solved for VC of 0 minus. And yeah, I know I'm not answering the questions on the slide, but I know where I'm going with this. So this is VC of 0 minus. The thing that we use, the new idea from this class, if you took 188 from me, it wouldn't have been such a new idea, is that capacitors are DC open. That's the thing you have to remember. Okay, that's great. We know everything we need to know for that circuit. I hate doing it like this. I want my whiteboard back. Okay. Now the next thing that's going to happen is the switch is going to instantaneously, taking 0 amount of time, move from position 1 to position 2. One little infinitesimal array of current. And we talked about this yesterday. Energy in a capacitor is stored in the form of charge. It takes time for charge to move. So it's going to take time for the voltage across the capacitor to change, because the energy in a capacitor is 1/2 CV squared. So for the energy to change, the voltage has to change. So the voltage across the capacitor cannot change in an instantaneous piece of time. We've already solved for VC of 0 minus. It is 240 volts. So we know VC of 0 plus. The current out of that capacitor can change instantaneously, and it will. Initially, when we looked at that, the capacitor was an open circuit, so the current through the capacitor at 0 minus was 0. Okay. Good thing to know to move on and to solve this circuit. So the next thing I want to do, I've got everything I'm going to learn from the 0 minus circuit, so I'm going to draw the circuit as it appears right after the switch is thrown. Now, right after the switch is thrown, we've had a big change in the conditions of the circuit, so the capacitor is no longer an open. My capacitor is a capacitor. We know the voltage across it because we've solved for that. It was 240 volts with the plus pointing up. And now that we're in position 2, R2 is in the circuit, and R2 is 12 ohms. Okay, what's going to happen? How much current's going to come out of that capacitor? I have no idea just looking at the capacitor. I'm going to have to go back and look at the resistor to help me figure that out. Ohm's law is always golden. I will quote this to I don't know how many times with my seniors. Everything starts with Ohm's law. Okay. I know the voltage across the resistor. These two are in parallel, so they share the same voltage. The pluses will be in the same direction. This will also be 240 volts because they're in parallel. I've got the voltage, I got the resistance, I can find the current. And this is just Ohm's law. If you're not sure about something in a circuit, look at the resistors. They're usually the easiest thing to figure out. And I get the current is 240 over 12, and that is 20 amps. Wow. So the current at 0 minus was 0. And in that instantaneous, infinitesimal bit of time when I threw the switch, it jumped to 20 amps. I got a huge current spike out of it. And when I put this in position 2, now R1 is dangling, so no current can flow through that one. So this is what I call my T equals 0 minus circuit. You'll see the method, the madness in a few minutes. We figured out what the current is at T equals 0 minus. What's the next thing I'm supposed to say? I'm trying to do this in order. Okay. We want to figure out what happens after this has been sitting here for a long time. Now, at T equals infinity, the capacitor's been sitting there with no change on it for a very long time. So it goes back to being the DC model of being an open circuit. The switch is still in position 2. So I'm connected to that 12 ohm resistor. This is what my circuit looks like at T equals infinity. So what am I expecting here? What do you think the current is going to be?
0?
Yes, you've got no energy source. It is 0. I equals 0 and VC of infinity equals 0. Okay, what happened between there? I initially had 240 volts. The 240 volts, this was at, I hate to do this to you guys, I'm going to confuse people. 240 volts at T equals 0. I have 0 volts at T equals infinity. Okay, what happened to all that voltage? In a capacitor, there's this wonderful equation for capacitors that comes up a lot. Q equals CV. So the energy is in the form of charge. So I've got capacitance, I've got charge on here. Well, as the when I initially have this thing at 240 volts, I've got 20 amps of current coming through here. And current is dq dt. It's the movement of charge with time. So if I'm putting current through this resistor, I must be pulling charge off of this capacitor. And as I pull charge off the capacitor, I'm going to, the capacitance stays constant. So the only thing I can do is lower the voltage. Where the energy goes, the energy that was initially stored in the capacitor, is it gets dissipated in heat through the resistor. And you're probably familiar with that from the 188 lab. You'd occasionally feel your resistors start to warm up. If they get warm enough, they explode because there's only so much heat that package can take. So it's the energy from that capacitor is going to be dissipated into heat through that resistor. It's all going to go away. So I initially have 240 volts. It's going to decay to 0 volts. And I'm just going to declare this. I'm not going to try to prove it at this point. You get a physicist to try to prove it to you. What's going to happen if I plot VC as a function of time? It starts out at 240. It's got to go to 0. and those are in volts. And it's going to decay exponentially. That's my best attempt at a exponential with this pen. Okay. How fast is it going to decay exponentially is the next question. We know that this is what's going to happen qualitatively. We're not too sure how it's going to get there and how fast. Yeah. I didn't want to do this yet. I was ready to do something else. Okay, we'll just leave that as an open question for now. Now we have a new event. What I'm going to do here with this analysis is I'm going to start out at some arbitrarily defined t equals 0 with the switch in position 2. And it's going to instantaneously move back to position 1. So I'm going to go through the same process. The last time, the first thing I did is I drew the t equals 0 minus circuit. If you follow these steps, it will make things a lot easier. So t equals 0 minus, capacitor's been sitting there a long time. DC model is an open circuit. Resistor, 12 ohms. There's no energy source in the circuit. There's no path for current to flow. So I can pretty safely say the voltage across the capacitor is right here. My VC of 0 minus in this case is 0 volts. And there's no current flowing. Okay. So I'm going to flip the switch. I'm just going to do this all without changing slides. That's my eraser. I'm going to flip the switch and throw it into position 1. My t equals 0 plus circuit. This is right after I flip the switch. I've got the 240 volt source in there. I've got the 6K ohm resistor. And I've got a capacitor that has no charge stored across it. So this is 0 volts. I can again go to KCL because I know 2 out of the 3 voltages on there. The voltage at 0 plus has to equal the voltage at 0 minus. So 0 plus, because I can't move charge off of there without time elapsing. Okay, I know 2 out of the 3 voltages. I can write a KCL equation. And that's going to be, oh no. Okay, you guys don't know about this yet, except for maybe Lauren and everybody who's in 110. My computer just froze. I will be back. I'm on slide 15.
Okay. I mean, I can still see and hear you like moving around. So
you can see and hear me, but the problem is I can't see my slides change.
Okay.
It's my computer it's my computer that's frozen. Okay.
Alrighty.
Give me about 30 seconds.